And now in this lecture we'll find out the area of a circle using two different methods. In the drawing we have a circle and this is square ABCD. We know that this is line segment AP is equals to 1 unit in its length. This is line segment QC that is equals to 3 units. Again, our mission is to find out the area of this circle. So we start with the first method. So ABCD is a square, so all those four angles inside square ABCD are right angles. Okay, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we will define the center of this circle. This point is point O. We will define the point of tendency of this tangent AB with this circle. This point is point S. And we join points O and S together by a straight line. Line segment OS starts from point O, that is the center of this circle, and ends at point S, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore OS is the radius of this circle. We find the radius of this circle as x. So S equals to x. So here we can implement rule 1. So I click quickly on rule 1. According to rule 1, a tangent for a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and this is tangent AB. That is tangent to this circle at this point, point M. In addition, we have also the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency, tangent AB, in this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OS that is equals to x. The radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by a straight line. OQ is of course the radius of this circle, that is equals to x, according to our definition. Here we can implement rule 1 again, because we have the radius OQ that is drawn to point Q, that is the point of tendency of tangent BC with this circle. Whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule 1. So inside polygonal SOQB we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral SOQB, inside this quadrilateral we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be tesseract again, not a square. So we relate to this quadrilateral SOQB is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SOQB, side SO must be equal to the opposite side QB. But SO equals to X, therefore QB must be also equal to X unit in its name. Likewise, according to the same rule, in the same rectangle SOQB, side OQ must be equal to the opposite side SB. But OQ equals to X, therefore QB must be OQ equals to S, therefore SB must be also equal to X unit in its name. So if we found out that quadrilateral SOQB, this quadrilateral, is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square equals to X units in its length. Okay. We also know that in square ABCD, all of its sides are equal to each other. That is to say, side AB equals to side BC equals to side CD equals to side DA. And especially side AB equals to side BC. So I write it down. In square ABCD, side AB equals to side BC. Side AB in total equals to AS plus SB. Again, AB equals to AS plus SB. AB equals to AS plus SB. And it is equals to this side BC. BC in total equals to BQ plus QC. BC equals to BQ plus QC. So in total, according to equation 1, we have to find out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB. SB equals to X. And it is equals to BQ. BQ equals to X. Also, plus QC. QC equals to 3 units in its length, according to what is given as the question. So in total, according to equation 1, we actually found out that AS plus X equals to X plus 3. Here we subtract X from this equation, equation 1. So X will get cancelled. And we left only with AS, that is equal to 3 units in its length. So if we found out that the missing 97 AS is equal to 3 units in its length. This is 97 AS, that is equal to 3 units in its length, according to equation 1. In the next step, we will do a construction, that is to say from this point P, we will draw a perpendicular on the radius SO. Again, from point P, this point P, we will draw a perpendicular on the radius SO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from this point P and side SO. This point is point N. When doing this construction, we're gonna do the small quadrilateral AP and S. Inside this quadrilateral we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this surface angle. In total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this surface angle must be equal to 90 degrees in its size. So inside this small quadrilateral AP and S, we have 4 rectangles. And according to rule 5, any quadrilateral that has 4 rectangles must meet this rectangle plus a square. So we relate to this small quadrilateral AP and S is a rectangle because it has 4 rectangles. So I can know this small quadrilateral AP and S is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle AP and S, side AP must be equal to the opposite side NS. But AP is 1, therefore NS must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle AP and S, side AS must be equal to the opposite side PN. But AS is 3, therefore PN must be also equal to 3 units in its length. What is the length of the missing 9 segment NO? From the moment it is very easy to see that NO in total equals to SO minus SN. Again, SO minus SN equals to NO. So what is known? NO equals to SO minus SN. So NO in total equals to SO. SO is the radius of the circle that is equals to X minus SN. SN equals to 1. So in total NO equals to X minus 1 units in its length. This is 97 NO that is equals to X minus 1 units in its length. In the next step, we join points P and O together by a straight line. Line segment PO is of course the radius of this circle. This is equals to X. In the next step, I'll copy this right green triangle P and O in a new page, and we'll implement the Pythagoras theorem on this right green triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So finally, this is the right green triangle P and O that I copied from the original drawing. according to the Pythagoras theorem, this right triangle PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. So I write it down. PO squared, that is the square of the hypotenuse, is equal to Pn squared plus NO squared. PO is x, therefore PO squared is x squared. And it is equal to Pn squared. Pn is 3, therefore Pn squared is 3 squared, that is 9, plus NO squared. NO is x minus 1, therefore NO squared is x minus 1 squared. So in total, according to the Pythagoras theorem, we have triangle PNO, we found out that x squared equals to 9 plus x minus 1 squared. So x squared equals to 9 plus x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, plus 2 times x times 1, that is minus 2x. So here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancelled x squared, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, plus 2x. So in total, according to the Pythagoras theorem, we found out that 0 equals to 10 plus 2x. Here we add 2x to this equation, and we get that 2x equals to 10. Here we divide this equation by 2, and finally we get that x equals to 10 over 2, that is 5. So if we found out that the radius of this circle x equals to 5 units, our mission is to find out the area of this circle. Actually, the area of any circle is equal to pi times the radius of the circle squared. So write it down. The area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of the outer circle must be equal to pi times the radius of our circle, that is x squared. So it is pi x squared. And we also right now found out that x equals to 5. So the area of our circle must be equal to pi times 5 squared, because x is 5. 5 squared is 25, so in total this expression equals to 25 pi. 25 pi is 78.54 square units. So if I found out that the area that you are looking for in this question, that is the area of this circle, equals to either 25 pi square units. In terms of numbers, the area of this circle equals to 78.54 square units. So finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. So ABCD is a square, therefore all those four angles are right angles. So actually this is a right angle. This is a right angle. This is a right angle. Finally, this is also a right angle. In the next step, we'll focus on this point, point B. Point B is defined as a common external point in relation to this circle. So from this common external point, point B, we have but before that, we will define the point of tendency of tangent AB with this circle. This point is point S. And we define the center of this circle. This point is point O. So from this common external point, point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ. So I keep clicking on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing, we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two they are equal to each other. That is to say, PA equals to PB. Okay, actually, implement rule 2 in our drawing. In our drawing, from this common external point, point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. And that is to say, BS equals to BQ according to rule 2. So I write it down. BS equals to BQ according to rule 2. So actually, if we define the length of this tangent BS as x, then the length of this tangent BQ must be also equal to x because they are equal to each other according to rule 2. We know that in square ABCD, side AB equals to side BC. So I'll write it down. In square ABCD, side AB equals to side BC. AB equals to AS plus SB. Again, AB equals to AS plus SB. AB equals to AS plus SB. Here AB equals to BC. BC in total equals to BQ plus QC. Again, BC in total equals to BQ plus QC. Again, BC in total equals to BQ plus QC. So according to equation 1, we should find out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB equals to X. And it is equals to BQ also equals to X. Plus QC equals to 4 units in its length according to what is given as the question. So in total, according to equation 1, we actually found out that AS plus X equals to X plus 3. Here we subtract X from this equation, equation 1, for x we get cancelled, and we're left only with AS that is equal to 3 units in its length. So if you found out that the missing line segment AS equals to 3 units in its length. This is line segment AS that is equal to 3 units in its length. In the next step, we'll extend line segment AD or side AD by a straight line until it touches the circle. And we'll define the touching point of the extended line segment AD with this circle. This point is point M. In the next step, we'll focus on this common external point, point A. Again, point A is an external point in relation to this circle. So from this common external point, point A, we have tangent AS, and from the same common external point, point A, if we draw a straight line M, if we get here, the straight line will cut the circle at 2 points, P and M. So from the same common external point, point A, we have also chord PM. Therefore, we can implement here rule 10. So if it equals rule 10, according to rule 10 is true in any circle. So in any circle, if AB is any chord, AB is the chord of this circle, and PT is a tangent to the circle. This is tangent PT, this is tangent to this circle at point T. So in this moment, the following equation is true. That PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So actually, according to this rule 10, if we have the common external point, point P, and from this common external point, point P, you will draw a straight line that cuts the circle at 2 points A and B. In this way, we get a chord AB, and from the same common external point, point P, we have tangent PT, that is tangent to this circle at point T. Then in this moment, the following equation is true, that PT squared equals to PA times PB. We can definitely implement rule 10 in our drawing. In our drawing, as I already mentioned before, if we focus on this common external point, point A, from this common external point, point A, we have tangent AS that is tangent to this circle at point S. From the same common external point, point A, if we draw a straight line, here it will cut the circle at 2 points, P and M. So in this way, we can then chord PM. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true, that AS squared equals to AP times AM. Again, AS squared equals to AP times AM. So I write it down. According to rule 10, AS squared equals to AP times AM. Because again, actually, if we focus on the common external point, point A, according to rule 10, the following equation is true, that AS squared equals to AP times AM. AS is 3, therefore AS squared is 3 squared, that is 9. And it is equals to AP is 1 times AM. AM in total equals to AP plus PM. Again, AM in total equals to AP plus PM. So according to equation 2, according to rule 10, actually found out that 9 equals to 1 times AP plus PM. Actually, when you multiply anything by 1, it will not change the value of the expression. So you can ignore 1, or if we multiply, if we open the brackets, you will get that 9 equals to 1 times AP plus 1 times AM is PM. So you can grow in 1 and you get that this expression in total equals to 9 equals to AP plus PM. 9 equals to AP plus PM. So 9 equals to AP . 9 equals to AP, that is 1 plus PM. So in total we found out that 9 equals to 1 plus PM. Here we subtract 1 from the equation and you get that PM equals to 9 minus 1, that is 8. So we found out that the length of this chord called PM is equal to 8 units. In the next step, we will do a construction. That is to say, from this point O, that is the center of the circle, we will do perpendicular on chord PM. Again, from point O, we will do perpendicular on chord PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and call PM this point as point N. So actually, we go perpendicular ON on chord PM. That is to say, from the center of this circle, that is point O, we go perpendicular on chord PM. And therefore we can implement here rule 11. So I'll repeat again a bit quicker on rule 11. According to rule 11, the perpendicular to a chord drawn from the center of the circle bisect the chord. So in the moment we have a circle, point O is the center of the circle, AB is a chord in this circle. So from point O, we do perpendicular OM on chord AB. Again, from point O, that is the center of this circle, we do perpendicular OM on chord AB. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And according to this rule 11, the perpendicular ON that is drawn from the center of the circle, that is to say from point O, bisect chord AB. That is to say, the perpendicular OM that is drawn from the center of the circle, that is point O, will bisect chord AB. That is to say, perpendicular OM divides chord AB into two halves. Each half equals to AB over 2. So the first half is AM, that equals to AB over 2, and the second half is MB, that is also equals to AB over 2. So repeat again. Perpendicular OM that is drawn from the center of the circle bisects chord AB. The first half is AM, and it is of course equals to the second half, that is MB, and each half equals to AB over 2. So we can definitely implement rule 11 in our drawing. Right in our drawing, from the center of the circle, that is to say from point O, we draw perpendicular on chord MP. So all the requirements of Rule 11 are satisfied. Therefore, we can implement Rule 11. According to Rule 11, the perpendicular ON bisect chord MP. That is to say, the perpendicular ON divides chord MP into two halves. Each half equals to MP over 2. So the first half is PN, that is equals to MP over 2, and the second half is NM, that is also equals to MP over 2. So I write it down. Perpendicular ON bisect chord PM. The first half is PN, that is equals to PM over 2. The second half is NM. Again, each half equals to PM over 2. So according to Rule 11, if we found out that Pn equals to Nm equals to PM over 2. But PM is 8, therefore PM over 2 is 8 over 2, that is 4. And from this whole equation, we derive that Pn equals to 4 units. Pn equals to 4. So this is line segment Pn, is equal to 4 units in its length. According to Rule 11. In the next step, we join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself. Therefore, OS is the radius of this circle. So, I write it down, OS is the radius of the circle. Here, the radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 1. So by doing this construction, we can do quadrilateral ANOS. Inside quadrilateral ANOS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth incident angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth incident angle must be equal to 90 degrees in its size. So inside quadrilateral ANOS, inside this quadrilateral, we have 4 right angles. And according to Rule 5, any quadrilateral that has 4 right angles must meet its right angle if not a square. So we relate to this quadrilateral ANOS as right angle because it has 4 right angles. Quadrilateral ANOS is right angle according to Rule 5. But we also know that the opposite sides of a right angle are equal to each other. So in right angle ANOS, side AN must be equal to the opposite side OS, but AN in total equals to 1 plus 4, that is 5, therefore OS must be also equal to 5 units in its length. But OS is the radius of the circle. So if we found out that the radius of the circle equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is 5, therefore the radius squared is 5 squared. 5 squared is 25, so in total this expression equals to 25 pi. 25 pi is 78.54 square units. So actually, in both methods, we found out that the area that we are looking for in this question, that is the area of this circle, equals to either 25 square units, so in terms of numbers, it is equal to 78.54 square units. So we'll finish with the first method. In the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, we found out the area of this circle using two different methods. So we start with the first method. In the moment you have a circle, and this is square ABCD, and this is line segment AP, that is equal to 1 unit in its length. This is line segment QC, that is equal to 4 units in its length. Again, our mission is to find out the area of the circle. So first of all, we know that ABCD is a square, therefore all those four angles are right angles. In the next step, we define the center of this circle. This point is point O, and we define the point of tendency of this segment AB with this circle. This point is point S. In the next step, we join points O and S together by side line. OS is the radius of the circle. We define the radius of this circle as x. So OS equals to x. The radius OS is 1 to point S, that is the point of tendency of tangent AB with this circle. And whenever your radius is 1 to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by side line. OQ is the radius of the circle, that is equals to x. The radius of Q is 1 to point Q, that is the point of tendency of tangent BC with this circle. And whenever your radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral OSBQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in every quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees inside. So inside the quadrilateral SBQO, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must meet this rectangle if not a square. So we relate to quadrilateral SOQB, this quadrilateral, as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle SOQB, side SO must be equal to the opposite side QB. But SO is x, therefore QB must be also equal to x units in its length. Likewise, according to the same rule, in the same rectangle SOQB, side OQ must be equal to the opposite side SB. But OQ is x, therefore SB must be also equal to x units in its length. So actually found out that quadrilateral SOQB is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Inside of the square, SOQB equals to x. So we know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC equals to side CD equals to side DA. And especially side AB equals to side BC. Okay, again, in square ABCD, side AB equals to side BC. AB in total equals to AS plus SB. Again, AB equals to AS plus SB, and BC equals to BQ plus QC. Again, BC equals to BQ plus QC. So in total, I should found that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB is x, and it is equals to BQ, that is also x, plus QC. QC is 3. So in total, we have found out that according to equation 1, AS plus x equals to x plus 3. Here we subtract x from this equation 1. So x will get cancelled, and we have to live with AS, that is equal to 3 in itself. So this is the resistance 978 AS, that is equal to 3 in itself. In the next step, we did a construction, that is to say, from this point P, we do perpendicular on the radius SO. Again, from point P, we do perpendicular on the radius SO. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SO. This point is point N. So by doing this construction, we added the smooth quadrilateral AP and S. Inside the smooth quadrilateral AP and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pins in total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pins must be equal to 90 degrees in its size. So inside the small quadrilateral AP and S, we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. Therefore, we know to quadrilateral AP and S as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AP and S, side AP must be equal to the opposite side NS. But AP is 1, therefore NS must be also equal to 1 unit in itself. Likewise, according to the same rule in the same rectangle AP and S, side AS must be equal to the opposite side PN. But AS is 3, therefore PN must be also equal to 4 units in itself. What is the length of the missing 97 NO? NO equals to SO minus SN. Again, NO equals to SO minus SN. So NO equals to SO. SO is the radius of the circle, that is X. Minus NS. NS equals to 1. So in total, NO equals to X minus 1 units in itself. This line find NO equals to X minus 1 units in itself. In the next step, we join points P and O together by straight line. PO is the radius of this circle, that is equal to X. So in the next step, I provide this line again triangle P and O in a new page and implemented the Pythagoras theorem in this right triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right again triangle P and O that are coming from the original domain. According to the Pythagoras theorem, in this right triangle P and O, PO square equals to PN square plus NO square. PO is x, therefore PO square is x square, and this is equals to PN square. PN is 3, therefore PN square is 3 square, that is 9, plus NO square. NO is x minus 1, therefore N square is x minus 1 square. So in total, we found out that x square equals to 9 plus x minus 1 square. So x square equals to 9 plus x minus 1 square. X minus 1 square is x square, plus 1 square, that is 1, minus 2 times x times 1, that is minus 2x. So here we have x square on both sides of the equation, so x square will get cancelled. Also we cancel x square on the side of the equation. On this side of the equation we left with nothing, that is to say 0. On the other side of the equation we left with 9 plus 1, that is 10 plus 2x. So in total we have found out that 0 equals to 10 plus 2x. Here we added 2x to this equation, and we found out that 2x equals to 10. Here we divided this equation by 2, and we found out that x equals to 10 over 2, that is 5. So we found out that the radius x of this circle equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So I'll repeat again. The area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. But x is 5, therefore x squared is 5 squared. So in total, the area of our circle must be equal to pi times 5 squared. 5 squared is 25, so in total the value of this expression is 25 pi 25 pi is 78.54. So in total, if you found out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 25 pi square units, so in terms of numbers, the area of this circle equals to 78.54 square units. We finish with the first method. In the next step, I presented to you how to find out the area of this circle according to the second method. So first of all, we know that ABCD is a square, so all those four angles inside square ABCD are right angles. In the next step, we define the center of this circle, this point is point O. We define the point of tendency of tangent AB with this circle, this point is point S. In the next step, we focus on this common sum point B. From this common sum point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to all two, they are equal to each other. That is to say, BS equals to BQ. So if you define the length of this tangent BS as x, then the length of tangent BQ must be also equal to x because they are equal to each other according to rule 2. Okay? So, we know that all the sides of square ABCD are equal to each other. That is to say AB equals to BC equals to CD equals to DA. And especially AB equals to BC. Put again in square ABCD, side AB equals to side BC. AB equals to AS plus SB. And BQ equals to BQ plus QC. Again, AB equals to AS plus SB and BC equals to BQ plus QC. So in total, AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is, plus SB. SB equals to X, and this equals to BQ. BQ is also X plus QC. QC is 3. So in total, according to equation 1, we actually found out that AS plus X equals to X plus 3. If subtract X from this equation, so X we get cancelled, and we left only with AS that is equal to 3 units in its length. This is 9/7 AS that is equal to 3 units in its length. In the next step, we extended 9/7 AD. This is 9/7 AD. We extended 9/7 AD by side line until it touches the circle at this point. We define the touching point of the extended 9/7 AD with this circle. This point is point M. So if you focus on this common sum point A, from this common sum point A, we have tangent AS, and if we draw a straight line from the same common sum point A, it will count the circle at 2 points, point P and point M. This way we actually created chord PM. So all the requirements of rule 10 are satisfied, and therefore we can implement the rule 10. According to rule 10, the following equation is true, that AS square equals to AP times AN. Again, AS square equals to AP times AM. So if you focus on the common sum point A, according to rule 10, the following equation is true, that AS square equals to AP times AM. AS is 3, therefore AS squared is 9. AS squared is 9, and it is equal to AP. AP is 1 times AM. AM in total equals to AP plus PM. So in total, we found out that 9 equals to AP, that is 1, times AM, that is AP plus PM. So 9 equals to AP plus PM. AP is 1, so 9 equals to 1 plus PM. If subtract 1 from this equation, and finally found out that PM equals to 9 minus 1, that is 8. So actually, this is called PM, that is equals to 8 units in its length. In the next step, we did the construction, that is to say from this point O, that is the center of the circle, we do perpendicular on chord PM. Again, from point O, that is the center of the circle, we do perpendicular on chord PM. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and 4 p.m. This point is point N. So actually, we have to draw from the center of the circle that is point O, perpendicular ON on 4 p.m. Again, from the center of the circle that is to say point O, we draw perpendicular ON on 4 p.m. So all the requirements of rule 11 are satisfied, and therefore we can implement rule 11. According to rule 11, the perpendicular ON that is drawn from the center of the circle, that is to say from point O, bisects 4 p.m. So perpendicular ON divides 4 p.m. into two halves. Each half equals to pm over 2. So the first half is pn, that is equal to pm over 2, and the second half is nm, that is also equal to pm over 2. So again, according to rule 11, perpendicular ON bisects 4 pm into two halves. The first half is pn, and this equals to the second half, that is nm, and each half equals to pm over 2. pm is 8, therefore pm over 2 is 8 over 2, that is 4. From this following equation, we derive that pn equals to 4. pn equals to 4. So this is line segment pn, that is equal to 4 units in its length. In the next step, we join points O and S together by side line. OS is the radius of this circle. The radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. Remember, you have radius that is drawn to the point of tendency, that is point S, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we're going to do quadrangle ANOS. Inside this quadrangle ANOS, we have 1, 2, 3 angles. This angle equals to 90 degrees according to our construction. This angle equals to 90 degrees because ABCD is a square, and this angle equals to 90 degrees according to rule 1. So in total, inside quadrangle NASO, we have 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle. In total, the mass will equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 facing angle must be equal to 90 degrees in its side. So inside quadrangle NASO, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this right angle plus the square. So we relate to quadrangle NASO. This quadrangle is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANOS, side AN must be equal to the opposite side OS. But AN is 4 plus 1, that is 5, therefore OS must be also equal to 5 units in its length. But OS is the radius. Therefore, the radius OS of this circle equals to 5 units, so the radius of this circle equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle, that is 5 squared. And therefore, the area of our circle must be equal to pi times 5 squared. 5 squared is 25, so in total this expression equals to 25 pi. 25 pi is 78.54. So in both methods, we found out that the area that we are looking for in this question, that is the area of this circle, equals to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. Okay, thank you very much.